this computer. All right. Let's very briefly, promised we would go ahead and look at the schedule and talk about our lazy programming assignment. It's due today. So anything that we need to talk about? Okay, so then we'll move on. Looks like everyone's okay on, oh, Ben, go ahead.
I just wanted to say I found this assignment really cool. I really like Haskell. Dipping in.
It is cool. It's fun, isn't it, to build these infinite data structures and then make it fast. And it's like you worry that something's gonna go infinite on you, but as long as you're just one step ahead, as long as everything's like one step ahead of where it needs to be, you're fine. Anyway, good. I'm glad you liked it. Okay. The other question, do we need to go over, so at this point you got, actually, you know what, I was gonna go over the type checking lab with you right now. But actually I think that we, in the interest of not polluting your brain with more than one lab at a time, let's go ahead and, there's no reason not to just delay that for a day or two. So we'll cover the type checking lab in more detail on Wednesday, okay? Unless there's any burning questions right now. But I'm gonna assume that there's not. Okay, so today we're gonna talk about type inference. So this is the last little section of material on typing. And so we're gonna be talking a little bit about the difference between parametric polymorphism and overloading, just to make sure that that's clarified in our minds. Then we'll talk about type checking, which is the lab that you will do, versus type inference. And type checking is a little bit simpler. Actually, it's a lot simpler. Type inference is a bit more complicated, as we'll see. Although it's still, interestingly enough, it's not too bad. Well, I should say, the basic version of it is not too bad, but surprisingly enough, I don't know, maybe it's not surprising. There's, as you get into it, it can get quite complicated. So we'll try to draw a distinction between type checking and type inference. Then we'll talk about basic type inference algorithm and sort of go over the basics of it. The point of this, I just want you to understand a little bit about what type inference is under the hood and how you might implement it. So we're not going to go too in-depth into this, but all right. So first, let's talk about parametric polymorphism versus overloading. So we've seen, as we've gone through Elm and we've gone through Haskell, we've seen these kind of cool parametric type systems where you can label, where we can annotate or infer types of things like functions. And so for example, you might have a function f here, and then we have a type signature, which is t to t. And we've sort of pointed out that t is a type variable. And what that means is that in the absence of any other constraints, you could replace t with any type, and that you would have the same algorithm. So this is called parametric polymorphism because the function is polymorphic, but it's parametrically polymorphic, so it's parameterized. And the function, and we're saying that this is true regardless of what the type parameter is. So why is this any different than overloading? Well, in overloading is like a much less general case. So in general, the idea of overloading is that a single symbol or function can refer to more than one algorithm, and like parametric polymorphism, each algorithm could potentially have a different type, and the choice of which algorithm you're going to run may be determined by a type context, but the types of the symbol may be arbitrarily different, and it doesn't generalize to all possible types. So for example, in the ML language, the plus function has only two types. Int to int maps to int, and real map to real. But there's no others. So that's just like this f up here, you could have int to int, or bool to bool, or string to string, or record to record, or hash to hash, or person to person, or database to database, or whatever. But in But here, the plus operator, the plus function, is only overloaded for two cases. So it doesn't generalize to arbitrary types. And so, like I said, so maybe the way I think about this is overloading is like a special case of parametric polymorphism. Go ahead, Eric.
So that's like one of the earlier labs that like parse, where we had many different parse functions, but it looked at the arguments that it was given and says, oh, I was given an int, run this one, or a pool, run that one.
Right, exactly. So we were doing, when we were building our interpreters in Julia, we were doing multiple dispatch, which in the context of this conversation is a lot more like overloading, because you had a version of a function and it required specific types. And if you didn't give it those specific types, like it didn't magically somehow generalize to other types. You could have multiple versions of a function, but they are all parameterized by specific types. So yeah, absolutely. Good. Okay, so I just wanted to make sure that we were clear on that. So when we think about type checking or type inference, there will be times when we'll end up mapping very specific sets of types to other specific sets of types, but there'll be times when we'll have type variables that can float around. And because the idea is that we want to be able to infer the most general possible type. By the way, here's an example of overloading. So you have like some add function, and you can give it integers. This is from a Pascal variant language, but you have an add function which accepts integers. Here you have an add function which accepts strings. This one returns an integer. This one returns a string. So this would be an example of an overloaded function. This is not parametric polymorphism. Okay, so with that in mind, let's think about the difference now between type checking and type inference. So in type checking, you have a program which has been annotated with a bunch of type annotations. And so for example, here we have a little chunk of C, where we have an F and a G, and we've got the return type annotated as int, and we've got the argument type annotated as int, and we've got the body of some function. And the idea is that, or maybe we've got this G which calls F, and we can use the type information in F and G, and maybe even a little bit of type information that we use from built-in operators like plus and things like constants, to make sure that all of the types that are being passed into all of the functions match. So this is the thing that you're going to code up for your last lab, type checking. You're given a bunch of annotations, and you just need to make sure that everything checks out. Type inference is a little bit different. So in type inference, we don't have type annotations, or at least they might be optional. So like in Haskell, your type annotations may be optional. So you might not have the return values, you might not have the argument types. And so we need to infer the most general possible types that could have been declared. And here, you can sort of imagine how that works. It's like, well, if you imagine just starting to analyze this little program here, if we were to remove all of the type annotations, start with saying, okay, there's some F, and it takes some parameter X. I don't know what this returns, and I don't know what type X is. Oh, but I see it's going to return, it's going to take whatever X is, it's going to add 1 to it. Well, I know that 1 is an integer, and I know that plus takes 2 integers. Therefore, I know that X must be an integer. Therefore, I know that the input type must be integer. And I know that the return value of this statement is going to be an integer. Therefore, I know that the return value of the function is an integer. It's this chain of reasoning that forms the backbone of type inference. And we'll see that it gets rather complicated, although straightforward, when we start to build up more complex expressions. But interestingly enough, languages like ML and Haskell are actually designed to make type inference feasible. Andy, go ahead.
When you talk about the most general type, is that the most specific general type? Because I'm thinking of a case where like your I don't know what we called it, type grammar, algebra, something. The one where like the different types can be of different other types. If you had something where, let's say that you've got an object, and an object can be either an integer or a string or a map or uh, an array or something, then in this case, the most general form of one is object. Like that's the most general thing it can be. And that would be that everything would just be object. But that clearly wouldn't work. So would you then like start at the top and go through and say, like, okay, well, let's see how specific can I get? Well, it can't be a string, can't be a list, but it can be these types of numbers, and then figure out. Do we try and find the most specific general?
Yeah, the most specific general type. Yeah, and there will be times when like a type inference algorithm run on something like the map function, it will only give us a type signature with parametric variables in it, meaning that any type could be used in the function. So yes. So for example, here we would probably infer just a general number type for these two lines of code, but we would not. Yeah, like if this is Julia, for instance, you might infer any, right? Like, well, X could be any, and then the return value would be any, and that'd be great, right? So yeah, it is. You're right that it's the most specific. Although I guess I'm not sure if the any object generically supports plus, so I don't know. Okay. By the way, so just so you're all, just so we all know, type inference, I think it's a very like it's not a cute language feature. I think programming language people really feel like this was an important language innovation because you get all the power of very cool, strong static typing and none of the overhead of type annotations. And actually, in fact, some languages like Rust, you cannot annotate certain kinds of things with the appropriate type information. I was reading about this earlier, and something like there's these weird closure examples where you can't annotate, like it's impossible for you to annotate the type of it, and so it has to be inferred for you, which I thought was kind of interesting. I don't fully understand why that is, but PL people really feel like this is an important language innovation. And it's improved steadily since it was first invented in the late 50s and early 60s. In fact, the history here is kind of interesting. It's an old idea, and so in 58 is when it first came out, and then was gradually improved over many languages. The version of type inference that most people use is called the Hindley-Milner algorithm. So this is from late 60s, late 70s. So this idea is almost as old as computer science itself, but and is under the hood in a lot of modern languages. Even you might not think about it, but it shows up most clearly in languages like Haskell, but other languages that you know and love use it as well. Okay, so type inference, the basic idea. Well, I guess we already sort of went through. This, but the idea is that we're going to try to annotate every point in an expression with some sort of type information. So here we might ask, what's the type of f? And the logic that we already sort of went through is, well, you sort of know something about the plus function. It requires an integer and an integer, and that's going to map to an integer. So the fact that the plus gives us this constraint means that this first parameter we know has to be an integer, and we know that this has to be an integer. And so because we know this has to be an integer, that tells us that this has to be an integer. And so now we know what the input type of the function is. Similarly, we know the return value of the function for similar reasons. But it gets more complicated as we get in. So the general idea of type inference algorithms is we first build a parse tree. And then we're going to start trying to assign these type variables to every node. And we're going to generate constraints. And each constraint is going to tell us something like a little piece of evidence about what we know based on our analysis of the parse tree. And there'll be some functions that we know, so things like tail. There'll be some built-in operators, which I guess you can think of just as another function. And there's going to be things like constants. And so we'll get all of these from from the environment, but we'll also just know some things about because of the form of the parse tree. So we'll know things like function application will tell us something about variables that are coming in and variables that are going out. So this is going to give us this whole bag of constraints. And then given those constraints, we have to actually finalize all of our type assignments. And to do that, we use a unification algorithm. So let me show you an example of what the constraints look like. So this is a kind of a busy slide. There's a lot of information here, but I want us to go through it kind of carefully. Now, I wish I had a whiteboard because ordinarily when I give this lecture, we take an expression and we start annotating it, and we start generating constraints, we start working through it. And today you're going to have to use your imagination a little bit. I thought about how to try to make this lecture work, kind of given the constraints of Zoom, and I think we're just going to have to talk our way through it. So, but Eric, go ahead.
I'm unsure because I haven't used PowerPoint in a while, but there might be like a pen tool. Might not be the most helpful, but you could potentially try to write something.
Yes, and I will try that. But I have found that it's difficult to write neatly.
Yeah, that is true.
Using PowerPoint. Maybe I'm just not that good at it, but it's hard. All right, so let's take a look at this. So this is a very basic table of constraint generation information. Oh, Andy, go ahead.
Zoom seems to have an annotation feature, and you can just place text and type in it like a text box.
Oh yeah, I see that. You know, I've never used that. Let me see if I can try that really quick.
I was playing around. I have a presentation I'm giving in another class. I was playing around with the annotation stuff today.
Okay. All right. Let's see. Can I get rid of that now?
There should be an eraser.
Okay. Got it. Okay. Well, we'll try this. Yeah. Maybe this will help. Okay. So let's go ahead and take a look at this table, and you'll sort of start to get the idea. So on the left is different expressions that we might encounter over the course of analyzing a particular program. So this particular table is for a very simple version of a language. It's a Lambda. It's like our little language that we built the interpreters for. So we've got things like, a function called add1. We've got the plus operator. We've got a 0 question mark operator. We've got these n operators, so n cons, n first, and n rest, as well as n empty. What this does is this creates a list of numbers. Okay, so this is like built-in functions that let us manipulate lists of numbers. We've also got an if statement here. We've got a lambda statement here, and we've got generic function application here. So these are the kinds, so on the left are the kinds of things that we might encounter. And on the right are the constraints that we can generate anytime we see one of those things. So for example, anytime we see an n, where n is a numeral, then we know that that thing is a number. And so we can annotate that parameter with a little, so this little double square bracket thing tells us, like this is showing us, this is like labeling a node. Okay, so we're gonna say that node n we can label with the constraint that it must be a number. And you might be thinking, well, this seems a little funny, but what will happen is we'll see that we can sometimes refer to the same kind of expression multiple times. And then when our unification algorithm comes into play, we'll see that a little constraint like this will tell us something about, for example, a function application. If we ever see a literal true or false, then we know that the type of those expressions are Booleans. Or like here's one. So if we ever see an add one and then e is some expression, then we actually get two constraints out of that. So the first constraint is we know that the result of the function, the type of the result is going to be number. And we also know that the type of the input expression must also be number. And so notice that this is true, this constraint over here on the right is true no matter what e is. And so one way in which we could check is, well, what if e was actually a constant number? So if it was a constant number, we would generate a constraint that said that this expression E was a number. And then we'd also have this constraint, which would say that it's a number. And those two constraints would have to agree with each other. So as long as this is a number here, they will agree, because this constraint and this constraint will say the same thing. But if we put a string in right here, then this constraint would say that it must be a number, or sorry, put a Boolean in. If we put a Boolean in here, then this constraint would say that it has to be a number, but when we actually parse and look at the Boolean literal, we'd get this constraint, which says that it has to be a Boolean, and those constraints would conflict, okay? So like I said, these little braces, these little square braces, it's like, think of them as referring to a specific point in the parse tree. All right, so similarly, if we ever see the plus operator, we see plus and two expressions, then we generate three constraints. We know that the result of the expression will be a number, and we know that both of the sub-expressions, the left-hand side and the right-hand side, their types must also be numbered. You can imagine what the 0 question mark thing does. So this accepts as input an integer and returns as output a Boolean. So the output type will be Boolean, the input type will be number. Let's go ahead and, I mean, I guess we can, well, I'll just keep working through this really quickly. I just really want you to get the idea. The most interesting things are down at the very bottom. So here's the cons operator for a number list. So if we ever call ncons, then we know that the result has to be a list of numbers, and the first thing has to be a number, and the second thing has to be a list of numbers. We know that if we take the first of an the first n first, if we call n first on something, we know that the result will be a number, and we know that the argument has to be a list of numbers. Rest gives us this, empty gives us this. N-empty is the number list constructor, which gives us, if we ever call it, it gives us a list of numbers. So notice that even though that's an empty list, there's only one kind of list in this little language. So it's still a list of numbers, even though it's an empty list. And so the typing will work out for us. All right, but let's look at the if statement here. So the if statement is a little bit interesting. If CTE, so C is the condition, T is, we'll call it the true branch, and E is the false branch. So take a look at this and tell me what is going on with the constraints that the if statement generates. I want you to think about this for a second. If we're going to do type check, if we're going to do type inference on something, what is how do we determine the type of an if statement if we're not actually executing code? What do you think? What is this saying, this line?
It's saying that the type of T and E are unknown, but they have to match. And because the type of the whole statement has to be the type of T and it has to be the type of E.
Yeah.
So whatever that type is, they have to be the same.
Right. So that's exactly right. So this is in the context of type checking and type inference, at least in this very simple example world, if presents a unique problem, because ordinarily you and I would like to maybe write code where we have an if statement, and depending on the condition, you might have the true branch or the false branch, and they might return different kinds of things. But if that's true, then it would be impossible to type check the language, to do any sort of type inference. And so in this particular case, we'll make a simplifying assumption. And the simplifying assumption is that no matter which branch of the if you take, you get the same type back, which is a little bit funny, but in this particular case, necessary, because it's such a simple language, and we're just, this is a very simple little type inference algorithm. Okay, let's take a look at lambda really quick. So lambda is the declaration of a function. And so if we ever see a lambda, we can say, well, the return type of this entire expression is, and notice the arrow here. So we've seen arrow now in Elm and in Haskell. And this is saying the type of this thing is a thing that takes things of type X and returns things of type B. Well, we don't know what those are, but this is a constraint, and this, hopefully other parts of our constraint generation algorithm will generate additional constraints on these nodes, and they'll tell us something more about it. Finally, if we ever see function application, then it's kind of interesting, but notice that the constraint that we generate is a little backwards. So when we see function application, then we know that the f, the type of the f, has to be something that takes something of type A and returns something of type f of A, which might feel a little funny. It almost feels a little backwards. But this is like I said, a little bit of the subtleties of constraint generation. So we've only got 5 minutes left, amazingly enough. So let's see if we can actually see this in practice. Okay, so oh man, this is going to be so hard. Okay, I'm going to try to do this. Here we go. We're going to try to use Andy's. So if I'm closing all my little windows. So if you feel like you need to say something, just barge in and say it, because I won't see you. I won't be able to see you raising your hand. All right. So okay. So here's our constraint generation system on the upper left-hand corner, and here's a little chunk of code that we would like to type annotate. Okay. So so let's kind of work our way through a couple of the obvious cases. So let me just what happened to my mouse? Oh wow. This, I'm so sorry, my cursor just totally disappeared. Not exactly sure what to do about this.
For some reason, it looks like it was like underneath the screen somehow. I don't know if that helps.
Yeah, I can't. Okay, hold on. Let me see if I.
Yeah, it's back.
All right, there we go. Yeah, I think moving the little windows confused it. Okay, we're going to try this again. There we go. Okay, so let's very quickly see what we can do. So this, we know clearly has got to be, we can annotate this with type number. So, oh wow, it disappeared again. Okay, let's try again. Hold on. Yeah. Stand by. All right, we're going to try annotating without being in, good grief, without being in full screen mode. Hopefully you all can see that. Here, let me just see if I can make it a little bigger. All right, we've got 3 minutes. We can do this. Actually, we can't. That's not nearly enough time, but we'll try. Okay, so we know that'll be a number. Let's see. We'll see things like we'll know that we'll know that that's a number. Let's see. So we'll know that. Let's think about the lambda here. So forget about the define for just a second, but we've got a lambda right on the outside, and according to our little chart here, lambda of x generates a constraint that says that the type of this whole thing is going to be a thing that maps whatever the type of X is to whatever the type of B is. So what that means is we're going to have a constraint that says that whatever the type of N is, so this whole thing is going to be something that's whatever the type of N is to whatever the type of the body is. And the body is this entire, it's this entire if statement. So let's see what the type of the if statement is. So the type of the if statement is, if we look over here on our little chart, we see that we know that this, the 0 bit has to be a Boolean, so let's assume that that's going to be okay. And we know that the entire type of the thing has to be the type of the first thing. So we're going to have a constraint that's going to be the type of the if has got to be equal to the type of the first node, which is called E. And similarly, the type of E in this case is the type of 1. And similarly, the type of that one node is number. So it'll sort of look like this, right? So if CTE will be, says that the type will be whatever the type of this thing is. The type of this thing will be the type of whatever a constant 1 is. The type of a constant 1 will be number. And so that will tell us that the entire return type of the if is going to be number. And that will tell us that this constraint here, the B constraint, will be number. So we'll know that that must be a number. And we're out of time. So darn, we didn't quite finish this. Sorry for the technical snafus. Hopefully, well, we're going to talk about this more on Wednesday because I want to work through this because I want to show you, I'll see if I can debug this a little bit more as far as the presentation style goes. But I want, because generating the constraints is only the first bit. The second bit that we need to do is actually working through the unification algorithm. All right, that's it we got. That's all I got for today. Take care. Have a great day. And plenty of, have a great day. And we will see you all on Wednesday.
See ya, Dr. Wingate.
See ya.